Alright, here's a problem that's fairly short. So basically we have a nilpotent element A in a ring. Of course, the reason we're using A to denote this ring is because it's commutative, and so the A really stands for abelian. Which doesn't really make sense because we don't really... Well, is the word abelian used to describe monoids? I'm not quite sure, because this is multiplication, it's not a group, it's a monoid. Anyways, so we have a nilpotent element and a unit. So this being a unit means that it has a multiplicative inverse, say u inverse. Yeah. And then we prove that u plus a is a unit. So observe that for any element b and any natural number n. Of course, natural numbers don't include 0. Although I guess this could be this. I think you could use well, if you used 0, then it would just be 1. Oh, well, then we'd have the sum from 0. I don't want to have to worry about that. Let's just say n in the natural numbers. 1 plus b. Oh, yeah, of course, that doesn't really matter because we're talking about nilpotency, and that means a to the n is equal to 0. And that's never going to happen for a to the 0 because a to the 0 is always going to be... It's either going to be... I don't think we define a to the 0... For rings, I don't think we define a to the 0 because when we say a to the n, we just mean you take a and you multiply it by itself n times. And so we haven't gone through any work of trying to define what it would mean to take a to the power of 0. I'm sure that if we were to define such a thing, the only way to make it well defined would be to set a to the 0 equals 1. But anyways, that's a whole side discussion. I don't really care about that. Anyways, so notice that if we take this 1 plus b here and multiply it by the sum from 0 to n of... Oh. Oof. Okay. So here, we, b to the 0 is going to be defined to be equal to 0. And we're not going to, So basically all we're doing here is we're just using b to the 0 as a placeholder for 0. We're not, defining, or we're not, making a... Yeah, this is just a convention. We're not, proving anything, special about it, I don't know. Just when I is 0, just pretend that this isn't b to the 0. Pretend that it's just 0, basically. So that... Wait, if that's 0... No. What am I doing? This is 1. So that when I equals 0, we're just taking 0, negative 1... The 0 is 1, so it's just going to be positive 1. So anyways, when you multiply these two things together, you're going to get 1 plus the negative 1 to the n times b to the n plus 1. That's because this is, we're basically going to get... It's not going to be quite a telescoping series, like you would see in Calc 2, but it's like if you would write all the terms out, then basically what we're going to get is this 1, when we distribute this 1 is going to account for this entire sum here. Then plus b is going to be this entire sum, but then you add an exponent, or you increase the exponent of all the b's by 1. And so what will happen is because of this alternating negative 1, all of the middle terms are going to end up canceling if you were to write this out. And the only things that would be left over is you'd have this term 1 here that you get when you multiply 1 by here where I equals 0. And then you're going to get the term that happens when you take b here and multiply it by the term in this sum when I is equal to n. And so that's going to be these two terms. So if... With that being said, if we have a natural number m such that b to the m is 0, then the sum is going to be, well, we just plug it into the formula. But since b to the m is 0, multiplying both sides of this by b gives us b to the m plus 1 equals 0. And so this whole term here is 0, and so we have just 1. So since A is a commutative ring, 1 plus B has multiplicative inverse given by this sum. And the reason I mentioned commutativity here is that like in non-commutative rings, you do have to worry a little bit about left inverses and right inverses. Because to have an inverse, not only does AB have to equal 1, but BA also has to equal 1 in order for A and B to be multiplicative inverses of each other. So anyways, by commutativity, we know that 1 plus B has a multiplicative inverse given by this sum. Okay, so that's for 1 plus B. Now the given problem, we want a inverse for U plus A. So instead of, so we know what happens when U equals 1. Now we have to know what happens when U is any unit. So what can we do? What we could do is we can factor out a U out of here, and this will become U times, well, this term is just U, so that becomes 1. And the way we factor out a U from A is by multiplying A by the inverse of U, which we know exists since U is a unit. And we can write this as A U inverse or U inverse A, doesn't matter, we have commutativity. Since A is nilpotent, so there's some n, let's say A to the n is 0, and since the set of nilpotent elements is an ideal, I don't even need that. Because what I think when I was writing this, what I was thinking was like, okay, well, since A is nilpotent, A to the n is 0, so then AU inverse to the n is going to be A to the n times U inverse to the n, but that's going to be 0 times U inverse to the n. But then I thought, wait a minute, we've already proven that's either another exercise or something that we proved in class, or both, that the set of nilpotent elements is an ideal. And so, since it's an ideal, we don't even need to do that calculation. We know automatically A is nilpotent, and the set of nilpotent elements is an ideal. So AU inverse is also in that ideal of nilpotent elements, i.e., AU inverse is also nilpotent. Okay, so that's nilpotent, so that's good. And we know by our previous paragraph, 1 plus AU inverse has some inverse, which we will call V. Of course, if we used A to the n equals 0, then we could write V as being the sum from I equals 0 to n of negative 1 to the I, AU inverse to the I. But we don't need to do that since we're just going to blindly apply the theorem without. We don't need to know the specific form of this inverse because we don't really use its actual structure at all. All we use is the fact that it's an inverse, and so we don't really care about what it looks like. That just adds clutter to the proof. But anyway, so by the we know that 1 plus AU inverse, because AU inverse is nilpotent, we know that this thing has some inverse, which we will call V. So what happens if we take U plus A and multiply by U inverse V? Then remember, we can rewrite U plus A as U times 1 plus AU inverse. And again, we're multiplying by U inverse V. Now we just move everything around. We get the U inverse by right next to each other, and we get the 1 plus AU inverse next to the V. These two things are inverses, so it becomes 1. These two things are inverses, so it becomes 1, and so this is just 1. And then, of course, by commutativity again, U inverse V times U plus A is also going to equal 1. And so therefore, U plus A has an inverse, namely U inverse V. And hence, U plus A is a unit. And that finishes up this proof.